Okay, so I think we shall start now. More people will join as we get into the talk. So, good evening, all. A warm welcome to all of you on behalf of the Department of Physics of Abhayapuri College. So, today we have the third talk of the online talk series, Current Trends in Physics. And today's topic is future astrophysics of compact objects, especially white dwarfs, neutron stars, and black holes. And we have with us today's speaker all the way from South Africa, Dr. Surajit Kalita. So we are very much thankful to him for agreeing to our proposal on giving us this talk. Uh, yeah, with this, I would like to thank the speaker again and all the participants. And I would like to request my colleague, Dr. Dipsika Gogoi, to briefly introduce the speaker with us, and then we can get into the talk. Yes, Dipsika, over to you.
Yes, thank you, Debabrot. So, good evening to everyone. This is the third talk, as Debabrot has already mentioned, of this online talk series. And before the talk begins, I would like to introduce today's speaker, Dr. Surajit Kalita, to all of you. So, Dr. Surajit Kalita completed his graduation in physics from Hansraj College, which is one of the best colleges in India of Delhi University. And then he did his post graduation from IIT Madras, and he carried out his PhD at Indian Institute of Science, IISc Bangalore. And currently, he is a postdoctoral research fellow at the Cape Town University of South Africa. So, it is our pleasure that we have him as a speaker today among us. And with this brief introduction, I would like to request Dr. Surajit to start his today's talk, which is entitled as Future Astrophysics of White Dwarfs, Neutron Star, and Black Holes. So, Surajit, over to you.
Yeah. Thank you,
Yeah,
Dipsika, and thank you,
Surajit.
Devbrat. Yeah, yeah.
Yeah, just one
I'm to
minute.
share my. Okay,
Yeah,
sure.
yeah. You just share your screen. Yeah.
Okay. I think
Yes.
it's visible, right?
Yeah, it's visible. So, Surajit, just 1 minute before
Yeah,
you start. So,
yeah,
so
sure.
we have several participants outside of Assam today from different institutes and universities. So I would like to request if they have any question in between the talk, I think they can raise their hand and write down their question in the chat box, or at the end of the talk, they may also ask the questions. So is it all right, Surajit?
Yeah, that's fine. Whenever you have any doubt, please ask me the questions. I'm
Yes,
absolutely
sure.
fine with that.
Okay, then the floor is yours, Surajit. Yeah, please.
Okay, yeah. So thank you, the organizers, for this nice invitation, and it's my pleasure to give a talk. It's my first time I'm giving a talk in a college in Assam, actually. So yeah, so this is the topic title of my talk, which is basically some astrophysics I'm going to discuss related to white dwarfs, neutron stars, and black holes. And as mentioned, I'm a postdoctoral fellow at University of Cape Town in the Department of Maths and Applied Maths. And yeah, I'm also a member of something called Hyrax Telescope, which I'll be talking just in one slide towards the end. And yeah, so let's me start. So this is our university. This is our University of Cape Town. Some buildings, you can see mountains and all these things. And these are nice scenery of some part of the Cape Town. You see nice mountain and beaches and all these things. But apart from this, we have nice telescopes, and astrophysics and astronomy is done in South Africa, which is quite advanced in terms of astrophysics, in terms of science in the world. I'm just showing you a couple of telescopes. One is something called radio telescope, and one is optical telescope. This is called Meerkat radio telescope, and this is called South African Large Telescope. Basically, it's in short, it's called SALT. So these are a few examples of the telescopes that South Africa has. Apart from this, there are many other things, and currently there are many other telescopes, and different progress are being made in South Africa. So let me introduce my title of plan of my talk. It's like I'll just give you a thorough introduction of the stellar structure. When I mean to the stellar structure, I mean to the structure of some compact objects. And in terms of compact objects, I'll just particularly focus on white dwarf, black hole, and neutron star. And apart from this, after giving some introduction related to this topic, I'll just show you something related to gravitational wave and something on radio telescopes, because these are two research topic where I particularly am interested in and I work on. But I'll not be talking about my research in advanced level. I'll just give you some introduction of these topics. Okay. So if you have any doubt at any point of time, because it might be quite new to you, whoever has doubt, please ask me. I'm fine with English, Assamese, Hindi, Bengali, whatever language you want to ask me a question. Okay. So let's go in the introduction. This is our sun, as we all know, and in the sun we are getting sunlight from the sun. So how are we getting these things? Because something called there is some fusion reaction is happening there, which means basically some hydrogen burning is occurring. Basically, what happens eventually? Basically, a few hydrogens fuse together to become a helium, and in this process, it emits some radiation here, which we see as a sunlight. So what will happen? Say, sun also has a particular amount of hydrogen. So after some time, of course, this hydrogen will be over because they will be fusing to helium and so on. So then what happens? So in that case, what will happen? Because most of the hydrogens at the core will fuse first, and towards the surface it will fuse later. The core will start having more helium compared to the surface, and the core will have more compact, and its temperature also increases. In such a scenario, even helium also fuse together, and which becomes something called proton-proton cycle. So where it becomes helium, helium can also fuse together to become beryllium, or become something like it becomes carbon or oxygen. So in this way, it can go massive and massive as the star becomes compacted hotter. Okay, so this is one brief idea how the stellar structure would look like. Stellar process would look like. Here it's the sun, where only these things are currently happening. But in the future, these kind of reactions we might be able to observe. So this gives me the idea of the life cycle of a star. So, for example, I'm considering sun, and as I said, once the hydrogen burning is over, at the core it will over first, then at the surface. So the core will become here, and still hydrogen burning is going on towards the surface. So because of that, what happens? There will be more gravitational pull at the center and less gravitational pull at the surface. So eventually, its size increases, and because of and when size increases, this phase is called something called red giant phase. There are different types of red giant and so on. So I'm not going to talk about all those things. But what happened at some point, your core is becoming so strong and strong that core kindly getting detached from the outside surface, and outside is the matter is just shattering away, and we call this phase as planetary nebula, and the core that remains, that we see as a white dwarf. Okay, but it's very important that to become a white dwarf from sun-like star, the mass of the star has to be a relatively smaller one. I'll just give you the exact numbers in next slide. But suppose you have a massive star, then the mass of the sun. Okay, so in that case, what happens? This process is same. Rather than red giant, it becomes something called red supergiant, little bit bigger in size. But because it has more mass now, because of that reason, that detachment that happened with the core than the outside surface, that doesn't happen here in this case. And what happens? All the matter suddenly falls in the core, and it becomes something called supernova. Okay, and after this supernova, only the core remains again. And depending on the mass of the star, this core either becomes a neutron star or can be a black hole. Okay, so you see the final stages of white dwarf, neutron star, and black hole primarily depends on the initial mass of the star, whether its mass of the sun is of the order of solar mass or higher than that. Okay. So now let's get an idea what's the size of these compact objects. Let's start with white dwarf. So generally, white dwarfs are of the size of our Earth. Remember, the masses of this white dwarf are of the order of mass of the sun, like solar mass, but the size is quite smaller than our sun. So it's size of our Earth. So you can understand its density is quite high. Okay. And similarly, for neutron star are much more dense. It's just radius of around 10, 12 kilometers. So you can understand, say, for example, there is a city in Canada, Vancouver. So you can understand the size of a neutron star of the order of the size of one big city. Okay. Similarly, size of a black hole, that depends what's the mass inside the black hole. Basically, it depends on the mass. If the mass is higher, then the size, basically, with respect to size, I mean to say up to which we can see, because black hole means inside after some point you will see nothing. So how big that area depends primarily on the mass of the object here. Okay. So you can understand, you can see the masses or the size of these objects are quite small, and that's the reason we say white dwarf, neutron stars, and black holes as the compact objects, because they are compact in size. Okay. So let's now get an idea of some properties of these compact objects. So as I said, white dwarfs has mass of the order of mass of the sun. Similarly, neutron star has also the mass of the sun. But you can see white dwarf has radius of around more than 1,000 kilometers of the radius of the Earth, whereas neutron stars are much smaller, of the order of just 10 kilometers. So you can understand neutron stars density is quite higher than white dwarf's density. You can see white dwarf's density is less than 10 grams per cc, but for neutron star it's higher. Okay. And for black holes, as I have said, what's the size of the black hole, what's the size up to which we can see, that's basically called the event horizon, and that event horizon depends on the mass of the object that's reside inside the black hole. So it's proportional with this mass. Okay. And of course, there are two different kind of black holes, basically. One is called stellar mass black hole, and one is called supermassive black hole. What's the difference? Stellar mass black holes can be originated from the standard stellar evolution that I have said, that a sun, a star massive than sun, but after its life cycle is over, it becomes hydrogen, helium, all these burnings are over, it becomes a black hole. So those kind of black holes are called stellar mass black holes. Okay. But there is something called supermassive black holes. Generally, supermassive black holes reside at the center of every galaxy. Even at the center of our Milky Way galaxy, we have a supermassive black hole, which has of the order of this much solar mass. So this kind of supermassive black holes are less likely to be originated from a stellar evolution, because to get such a mass, your initial mass of the star has to be quite larger than this, and such stars have never been observed, and we know that it's not possible. So there are different theories people have proposed that might be originated from Big Bang and so and so. So, but I'm not going to discuss on this. But the supermassive black holes are actually much more massive compared to stellar mass black holes. Okay, and what is the progenitor mass? Progenitor mass means what kind of star will become a black hole, or what kind of star will become a white dwarf. So to become a white dwarf, the initial mass of the star has to be of the order of less than 10 solar mass. So our sun fulfills this criteria. So at the end of its lifetime, it will become a white dwarf. Okay. But for neutron star, the mass of the star has to be higher. It's like 10 to 25 solar mass, roughly. And for stellar mass black hole, it needs to be much higher. It's over 25 solar mass. So you can understand this difference. Although these numbers are quite vague, don't consider these numbers that exactly out of 10 it has to be neutron star and so on. So because you cannot see these things in a lifetime, we just need to do some computer algorithm that to make to understand this, because you require millions to billion years to observe all these things, which is not possible. And what are the temperatures? The temperature of the surface temperature of the white dwarf is of the order of 4 to 5 Kelvin. Central temperature would be larger than this, of course. but we generally observe the surface temperature from our telescope data. And for neutron stars, it's slightly higher than white dwarf's temperature of the order of 10⁻⁶ to 7 Kelvin. Okay. So these are some properties of these three types of compact objects. Okay. So another important thing that generally astronomers do, that's basically called the Hertzsprung-Russell diagram, or in short HR diagram, which basically plots, here basically we plot the temperature or the surface temperature of the star, and here on this axis we plot the luminosity of the star. Remember, the luminosity increases from bottom to top, but the temperature actually decreases from left to right. It's just a little bit of different conventions that people use. So on this branch, there are different branches you can see. So there is a branch at the middle. This is called main sequence branch, which means all the stars that are still emitting radiation by fusing its hydrogens, like our sun, they all fall here at this branch. Okay. However, as I said, it becomes something like giants, supergiants, and so then its position changes. It becomes on these positions. Okay. And at the end of its lifetime, when it becomes white dwarf, its positions comes here. Now let's see. For example, you see luminosity decreases. That means, see, white dwarfs are less luminous than our main sequence star. However, white dwarfs might have a higher temperature than our main sequence star because it's on the left hand side. Okay. And why I do people generally don't put neutron stars, because neutron stars are quite dim, so it will go much slower and at much higher temperature. Okay, so neutron stars are generally, they don't put neutron stars in this diagram. But you can understand this is basically in short HR diagram, which can be plotted for every stars, whatever phase it's in, you can plot it here. Okay. So next, let's come to the idea of the size of this object that I have said, like it's 1,000 kilometer, 10 kilometer, its masses are of the solar masses. So how to obtain all these things? So to obtain those things, we require something called hydrostatic balance equations. I'm just going to keep it very simple. So if you still have some doubt, please ask me. So what does hydrostatic balance means? It means that you have a star, for example, this is a star, for example. Say one of these compact objects, either white dwarf or neutron stars or black hole. Now let's consider any point, say this point. So it's in equilibrium. We see it's in equilibrium. It's not blowing up or it's not collapsing. Okay, that means there are two different pressures that needs to balance each other. So one is gravity. So we all know gravity acts inwards. Whereas, so to counter that, you need to have some gas pressure. So at the white dwarf, generally we have electrons. So electrons exert some pressure, and that's basically referred here as the gas pressure. So they balance each other. Okay, and once they balance each other, so the pressure giving by the force giving by the gravity has to be balanced by the outside pressure by this gas. Okay, so if you write it in terms of just simple equation, so force of gravity we all know from these things, it's given by minus g dm by r square. Dm is the small mass inside if you take a small annulus here, okay, of the size of dr. And this is the extra pressure dp. And similarly, if you can write dm, this is a very simple equation. What is the mass? Mass would be mass inside here. Suppose if I take a small annulus of radius dr, assuming its density to be fixed in the small annulus rho, and its area is say A, in that case, your total mass is given by the volume into density. So this is the mass. So you can rearrange these equations. You obtain two equations. One is called pressure balance equation and one is called mass balance equation. Probably you know mass estimate equations from your classical mechanics in class 9, 10 or so. It's very simple. dmdr is 4 pi r square rho. But the first equation is called pressure balance equation. And basically how the pressure changes, and you can see it's negative sign. That means pressure decreases as I go from inside to outside. Okay, and it's proportional to mass and density. Okay, So you have now two equations here, and these two equations needs to be solved to obtain the structure of this object. But you can see here I have how many variables we have. One is R, but R is independent variable. I'm not considering this. How many dependent variable? I have M, I have P, M, and rho. I have three variables, but I have just two equations. That means it's not exactly still solvable. I need one more equation. So how to obtain that equation? I'm not going to tell about that. So, so to obtain that equation, let's try to understand what's there inside a white dwarf. Because white dwarf has high density, because of that reason, something called, I'm just going it little technical here, but forget about that. It's basically electrons are fermions. So the electrons that's inside a white dwarf, they basically follow something called Fermi-Dirac distribution. And if you have studied some statistical mechanics, you know Fermi-Dirac distribution can be written in this form. But what happens now? You can for a white dwarf, you know the temperature because we see the temperature, and you know the Fermi energy because we know the density. You can always find this kind of relations for white dwarf at any radius. Okay, so KT is much less than Fermi energy. In such a case, this complicated looking expression simplifies to this very simple equation. That means it's just like a step function. It's 1 when E is less than EF, and when it's E is greater than EF, it's 0. What does it mean? Probably you have seen such curve in statistical mechanics, whoever has done in undergrad. It's very simple. If you just plot Fe versus this E here, you can see for different temperature, if the temperature is 0, then you obtain 1 and then it's 0, something like this kind of function. Whereas if you plot for other temperature, not 0 temperature, but some finite temperature, you can obtain this kind of curve. But now for a white dwarf, as I have shown, this approximation is perfectly valid. That means what I can say from here, that white dwarfs are cold, although white dwarf temperature is higher than our temperature of the sun, but because its the Fermi temperature is less, its temperature is less than the Fermi temperature, in such a case, we say that white dwarfs are cold. And that's why zero temperature calculation is a good assumption for white dwarf. So in the future, in the next step, I'm going to show whenever I'll write some integration, generally we need to write the integration, say from 0 to infinity. But rather than 0 to infinity, I'll just write 0 to some EF value, because after that, it's just 0, because after that, that integration doesn't contribute anything. Okay. So whatever integration I'm going to write, that's basically from 0 to EF or 0 to, some finite value. So it basically simplifies our calculation. And you can see, you can write the number density of electrons from phase space volume. And you can see the integration is now 0 to PF. I'm not writing to 0 to infinity because I don't write that big factor here. Similarly, we can write the pressure, and pressure and density are quite related to each other. So now one needs to solve this integration. It can be solvable exactly, but one can solve with certain assumption that suppose I have the electron gas that's inside the white dwarf are non-relativistic. In such a scenario, this complicated looking expression simplifies to this. And in such a case, you can show that pressure is proportional to density power 5 times. Similarly, for relativistic electron gas, this factor contributes more. And in such a case, your pressure is proportional to rho power 4 times, density power 4 times. So generally, I'm just saying that in astrophysics, people generally use to say like 5-third equation of state or 4-third equation of state or something like some other number. That means basically how pressure and density are related to each other. And this kind of equation of states are called something called polytropic equation of state. Okay, but this is just an assumption. One can solve exactly these things. And actually in 100 years ago, Chandrasekhar itself solved these things. And you can show that this is the exact relation between the pressure and density. You can still obtain those 5-third and 4-third equation of state just by putting x very less than 1 and x very higher than 1. But this is the exact expression. So what we now have, as I have said, I had dpdr and dmdr equations. But those equations are incomplete because I need one more equation. And that equation is now the equation of state, basically the relation between pressure and density. Now I have three equations, three variables. It's exactly solvable. And because these are differential equations, you require something called boundary conditions. So these are pretty simple boundary conditions. Mass at the center, of course, has to be zero because no matter. And towards the surface, whatever mass that we see as the mass of the star. At the center, density is maximum. Similarly, the pressure, you can obtain either this or this because pressure and density are related. But when I'm coming to the surface, pressure or density both basically gradually decreases to zero. Okay, so these are the boundary conditions. These are my three equations. I can now solve this set of equations exactly. And in such a case, I can obtain this kind of figure. That means, say I'm starting with some central density, which is of the order 10⁻⁷ gram per centimeter cube. Once you start solving the equations exactly, I mean numerically, from outside, inside to outside, your density decreases. And at this point, density becomes zero. And at that point, mass is turning out to be, say, 0.8 solar mass. So we say that the white dwarf, which has central density of 10⁷ gram per cc, has a mass of 0.8 solar mass and radius of 7,000 kilometers. Okay. So this exercise can be done for different central density. I can start with different central density here. And after calculation, we'll get different mass and different radius. Okay. So if you just combine all these plots, that means now here in this black curve, each point represents exactly one white dwarf. That means each point corresponding to one central, a particular central density. So each point, for each point, you have a certain mass and certain radius. And this curve was obtained by Chandrasekhar, as I said. And you can see a very interesting thing that when you are getting higher and higher, after some point, your mass doesn't increase anymore, even if you increase the density. And in such a case, this is called something called limiting mass, which is also called as Chandrasekhar mass limit, which is of the order of 1.44 solar mass, for which he later got Nobel Prize. And you can understand that the mass of this Chandrasekhar mass is a very fundamental thing because you can see all the factors: Planck constant, speed of light, gravity, mass of proton. So it depends everything on the fundamental constant, except this one quantity, which is mu e, which is basically depends on the material. So basically, if you have a carbon white dwarf, mu is 2 because it's called mean molecular weight per electron. So that means your mean molecular weight per electron for carbon, its atomic mass is 12 and atomic number is 6. So you have 12 by 6 is 2. So according to this, so once you take a different material, your Chandrasekhar mass limit will change. But this 1.44 solar mass, when you consider mu e is equal to 2. Okay. So now whatever I've said, that's only the dp, dr, and dm, their pressure balance equation, all these things I've said in the Newtonian case. What happens in GR case, I'm not going to derive any of the general relativistic things, but I'm just going to show you that this equation, the pressure balance equation that I have shown earlier, now modifies to a different form if you introduce general relativity rather than Newtonian mechanics. But your mass balance equation remains the same. It's still 4 pi r square rho. And this equation is called, famously called as Tolman-Oppenheimer-Volkoff equation, or TOV equation. So now I have these two modified equations basically compared to Newtonian case. And now if I do the same exercise again, writing basically obtaining the mass radius curve for each case, for each white dwarf, and you can see this is the final plot that we can get, where basically the red curve is the Newtonian case that I've shown you, that you can obtain that 1.44 solar mass Chandrasekhar limit, and the blue curve is the GR case. You can see at low density, they are overlapping each other. So there is no difference of GR or Newtonian case. That means general relativity can be approximated to Newtonian theory at low densities. But only at high density, you can see there is slight deviation. You can see there is a turn back that's been started here. And one can show that whatever mass, whatever white dwarfs are here, after this turn back, whatever white dwarfs fall here, they are basically unstable. So once they're unstable, basically they no longer exist in the nature. So your maximum mass that you can see in the nature is of the order of this, which is still 1.4 solar mass. But why GR is better than Newtonian? Just one small example. You can see in the Newtonian case, all the masses are still valid. You can still get, high density and low masses. Small white dwarfs. But you cannot go. The Chandrasekhar mass that 1.44 solar mass is actually a limiting case when you have infinitely high density or zero radius. But for GR, it's pretty simple that this mass limit is not necessarily needs to be going to infinitely density or zero radius. It's you can obtain it at finite density. So it's quite practical, and that's the reason GR is better than Newtonian if you try to explain white dwarf. And now, suppose you have a white dwarf here, but what happens if it accretes more mass, the white dwarf? In such a case, suppose you have a white dwarf here, and you have some main sequence star which has less gravity than the white dwarf. The white dwarf will start pulling out matter, but we know white dwarf has a maximum mass of 1.4 solar mass. So if it accretes more mass than this, so then it cannot no longer have that equilibrium structure, and it will burst out to produce something called type 1a supernova. Okay. And type 1 supernova are very important in cosmology because they are used as something called standard candles, basically standard ruler, to measure distances in cosmological objects. Okay. And how do you know that these are type 1a supernova? Because you can observe its spectrum, and if you see some silicon absorption line and no hydrogen line, you can roughly confirm that those are type 1a supernova. Okay. So that I have said about white dwarf. So what's about neutron stars? For neutron star, so the pressure balance and mass balance equation, dPdr dmdr equation remains the same, the GR ones that I have said. But your equation of state is now different because neutron star no longer contains only degenerate electrons, but it contains degenerate neutrons, protons, and many other particles. But what's there exactly, we still don't know. And because of that reason, we still don't know the exact mass radius curve. For white dwarf, we know that just one mass radius curve, which is Chandrasekhar mass radius curve. But here we don't know. And as a result, researchers have been proposing different material that can be inside a neutron star. And with respect to that, you obtain different mass radius curve for neutron stars. But some mass radius curves are ruled out. If your mass radius curve is something, say, for example, something comes here, but we observe a neutron star which is of the order of 2 solar mass. So that particular mass radius curve cannot explain this neutron star. So in such a case, those equation of states are ruled out, and only these kind of equation of states are valid, which basically gives you neutron stars of the mass more than 2 solar mass. Okay. So this is just a short, just one introduction of neutron star. So now I'm coming to black hole. I'm just giving you just quick summary from now on. So in a black hole, as I've said, black holes doesn't have any proper surface like white dwarfs and neutron stars, but we can see up to some radius. So that's basically called event horizon radius. And for a non-rotating black hole, this event horizon radius is proportional to the mass that's inside this black hole. Okay. But not only this radius, outside this radius, there are many other radius that are particularly interested for astrophysical scenario, something called photon sphere. So this is basically the photon last orbit. That means you cannot see photon after this. Similarly, something called stable circular orbit and bound orbit. So I'm not going to tell about all these things. There are many different scenarios, but these are all important once you try to explain some important phenomena for black holes. So for example, accretion disk and jet. So here accretion disk means, say, this is a black hole and there are some mass, some other object, and its mass being accreted by this black hole. And as a result, you see something like disk-like this structure, and this is called accretion disk. And because of some different mechanism, you see some other radiation is coming out of this accretion disk, and these are basically called jet. But to understand all these things, you need to understand all these radii, which are very much important. Okay. So far, whatever I'm telling about the structure of white dwarf, neutron stars, and black hole, those are basically non-rotating, non-magnetized white dwarf. But suppose I have a rotation of white dwarf, rotation also, which is of course been there with all the astrophysical objects. So no object can have like zero rotation or zero magnetic field. All objects have some rotation and some magnetic field. So what's its effect? You can see if I have a spherically symmetric object, say a white dwarf or neutron star, if it's rotating, say like in this object, in this orbit, in such a case, it's basically deforms and it becomes an oblate shape. And once it deforms, it acquires more area, more volume. In such a case, its mass also increases. So rotation can increase the mass of white dwarf or neutron stars. Similarly, for magnetic fields, also depending on the magnetic field lines, magnetic field structures, your white dwarf can have different shapes. And also magnetic field, because of exertion of extra magnetic field pressure, white dwarf and neutron star can also gain masses. So white dwarf and neutron star can become massive in the presence of rotation as well as magnetic fields. So what about black hole? For black hole also, this radius that I have said initially about event horizon radius, so those radii are no longer the same. The numerical value is not the same. So now they are increasing, and there are many different important concepts like ergosphere and so on are there, but I'm not going to discuss this. But this rotation is also important to know because probably you have seen such an image a few years ago when Event Horizon Telescope first discovered black hole. And you can see for this black hole, a part of the black hole is not as luminous as the other part of the black hole. This clearly indicates that this black hole is a rotating black hole. And this part is coming towards us, and this part is going behind us. And that's why rotation is quite important to understand the black hole structure also. Okay. So, so far we have studied so many important thing about important physics of white dwarf, neutron stars, and black hole. But not only this, but why these are important. Of course, many researchers are studying the structures of these objects. For example, as I said, radius, mass, and many other different disk and jet, and so and so. But there are many other objects. For example, supernova. I've just briefly mentioned about type 1a, but there are different kinds of supernova. So there are many different supernova that's there. So you need, if you want to understand the physical mechanism of supernova, you need to understand the structure of these objects also. Similarly, something called fast radio bursts. So these are basically fast radio bursts are basically some burst-like objects you see for a fraction of a second, but they are observed only at radio frequencies. Okay. And there are over 700 or so fast radio bursts have been detected so far. Similarly, something called gamma ray bursts. It looks like fast radio burst, like a burst, but it doesn't observe in radio frequency, but rather observed at gamma ray frequencies. And gamma ray bursts are more in number that have been observed so far. Similarly, accretion disk and jet that I have already told you. Pulsars. Pulsars are basically something called rotating neutron stars. That means there is a neutron star and its rotation axis is this, that means rotating in this way, but its magnetic field lines are not aligned to this rotation axis. In such a case, you see some kind of radio emission from here, and these are basically called pulsar. That means it's pulsating, basically magnetic field and rotation are pulsating on each other. Similarly, something we know about dark matter and dark energy, like we know that whatever we see in the ordinary matter, that's roughly about 5%, but we still don't know many other masses that is there in the universe are 20. I mean, these are called dark matter and dark energy. So to obtain, to understand these things, also you need to understand the structure of some, say, for structure of black holes also. Similarly, gravitational lensing, another quite interesting phenomena where basically you see multiple images of a single object. So for example, there is just an image of the sky and you see, say for example, 1, 2, 3, 4 objects. But these are basically not 4 objects, they are one object. But because of something called gravitational lensing, you see multiple images. Similarly, these are some lens galaxies. So to understand about gravitational lensing, you also need to understand about structure of this white dwarf neutron stars and black holes, and some other things also. So in that way, I'm just going to give you a brief overview, basically why the structures are quite important to understand many other things in astrophysics and astronomy. Now, how to observe these things? As I've said, we need to understand these things from different observations. So what are the different observations? So something called, as I've said, that first ray bursts are obtained by some radio frequencies, and gamma ray bursts can be seen by gamma ray frequencies, and so. But there are other frequencies, you know, these things that electromagnetic spectrum has all the radio to gamma ray. In between, you have X-ray, visible light, infrared. All these different frequencies are there, and we build telescopes to observe objects at these frequencies. Okay. It's important that some of the objects we build at the Earth, like these telescopes, whereas some of the things we send to the space, like Hubble Space Telescope or James Webb Telescope, and so on. So in such a case, why it's so? Because we have something called here ionosphere in the Earth atmosphere. So because of that reason, not all the radiation can reach to basically this Earth surface. As a result, say for radio frequencies can come to Earth surface or optical frequencies. So we build telescopes for these things at the Earth, whereas for other, for example, for gamma ray, X-ray, it cannot basically pass this layer, and as a result, we need to send telescopes, the observer, to the space so that it can observe objects at these frequencies. Okay. So these are electromagnetic spectrum, but not only electromagnetic observation, there are different observations. For example, neutrino observation. People are observing neutrino. This is something in Antarctica people have built, iceberg neutrino observatory. So in these things you can observe or you can detect neutrinos. Similarly, we have gravitational waves that we all know. We all know that people probably have heard that LIGO, Virgo detectors have observed lots of gravitational wave events over the past 5-6 years. So these are some kind of gravitational wave detectors. These are on the Earth, basically, a LIGO detector. But in the future, people are trying to send some spacecraft to the space, which are basically called, this is called LISA gravitational wave. So this will also detect some of the very interesting objects. So from now on, just I have a few slides left. I'm just going to discuss a little bit about these gravitational waves and something about radio frequencies, the radio telescopes that I've shared, I told you, because those basically on those topics I mostly work on. I don't work on neutrinos and other telescopes. So I'm just going to give you a brief overview of this radio telescopes and the gravitational wave, these telescopes. Okay. So let's start with gravitational waves. So the fundamental rule of the gravitational waves, what kind of system can emit gravitational waves? This is the primary thing, that if a system has something called quadrupolar moment, but it's non-zero and it's time varying. So any system which possesses such a criteria, it can emit gravitational waves. So probably you have heard in electromagnetic theory something called dipole radiation, dipole moment. So it's just one higher order moment that is basically called quadrupolar moment. And because of that reason, it's different with respect to electromagnetic radiation. So electromagnetic radiation are dipole radiations, where gravitational radiation are quadrupolar radiation. And as I have said, so far LIGO, Virgo, and Discagra have been detected many gravitational from merger events. That means you have two objects here which are rotating around each other. So let's consider two black holes which are rotating around each other. As a result, it's emitting some gravitational waves. And once emitting energy, they will start coming closer and closer. And once they're coming closer and closer, your amplitude of this wave and the frequency of the wave increases. And when they merge, you obtain the maximum amplitude of the gravitational waves. And after that, they merge and becomes one single object. And you no longer see much gravitational radiation after this. So LIGO and Virgo have been detected only this kind of gravitational waves at the time, which is produced at the time of merger. But in the future, they are still being upgraded, and they will eventually detect this kind of gravitational waves, which will be observed continuously for a long time. Okay. And as I said, like space-based detector LISA will be launched in over 10 years. So we have still some time. So what's the physical mechanism of gravitational wave detectors? So this is just one merger theory that I have just told you, that two objects are rotating around each other, each emitting gravitational waves, and at the time of merger, you see maximum gravitational waves. You also see some other waves like gamma ray burst and first radio burst, also this. And after this, you just have a remnant and it no longer emits any gravitational radiation. So this is basically the short of this merger theory. So how gravitational wave works, what's its principle? It's like, suppose you have a ring of particles. Okay. Now gravitational wave has two polarization. It's very similar to electromagnetic waves. In electromagnetic waves also you have two polarization modes. One is electric field and one is magnetic field, and they have a phase difference of 90 degrees. But in gravitational waves, there are two polarization. These are called H plus and H cross, but they have a phase difference not 90 degrees but 45 degrees. That means now if we have this kind of gravitation, beads of particle and the gravitational waves fall, say, onto the screen, then because of this plus component, if it changes the shape of the object with respect to time in this way, the cross will change the object shape with respect to this little bit of different shape. Like, and you can see this is just 45 degree to this. So they have a phase difference of 45 degree. Now, what LIGO-Virgo detectors have detected, so what LIGO-Virgo detectors have detected here, you can see these are two kind of arms which have basically lasers. Now, if gravitational wave falls here, because you have this kind of squeezing in one direction and elongation in the other direction, so one arm of that gravitational wave detector that will be slightly elongated and the other will be slightly squeezed. And as a result, you can measure that difference, and that's how people have detected this gravitational wave radiation. Okay. So, and so far people have observed lots of masses, lots of black holes, lots of neutron stars merger, and these are basically have been observed so far. But yeah, still we are yet to observe some white dwarfs in gravitational waves, and that will be done only by LISA, not by LIGO-Virgo Kagra things. Okay. And where we have these gravitational wave detectors, so far we have two LIGO detectors in the US, one Virgo detector. There is one something called geosignal. It's no longer that much of useful. It's in Europe. Kagra is in Japan, and LIGO India is currently built on. It will probably be operating in a couple of years or so. So we have that many gravitational wave detectors. Of course, it's less in number compared to other electromagnetic detectors, but this is quite new, and that's why we have less detectors. But in the future, it's being upgraded. Some of the space mission will be launched, so probably we'll see much more interesting objects in the future. And what is something called sensitivity of gravitational wave detectors? It basically means you have these curves are basically for lots of detectors. So for example, I'm just taking one curve. So for LIGO, this is the curve. Now, what kind of object it can detect? So for example, it can detect compact binary in spiral. So whatever objects are falling above this curve, it can be detected. So it's not visible here. So for example, for LISA, so it's here. This is the curve. So suppose I have a galactic binary, which has a strength of this much. So it can be detected by LISA. But suppose the galactic binary doesn't have that much strength and it falls here, then such an object cannot be detected by LISA. So that's how basically gravitational waves, what are the objects it can detect? So something like pulsars. Pulsars have not been observed directly by gravitational waves so far, detected because its sensitivity is less compared to the currently operating LIGO-Virgo. But once it's being upgraded to becomes advanced LIGO or becomes advanced Virgo, so then probably it can detect pulsars also in this way. So that's how basically over the time these gravitational wave detectors are detecting more and more number of objects and more different objects also. So this is just a brief overview of gravitational wave detectors. As I've said, I will also speak about radio telescopes. So probably have seen some kind of radio telescopes here. Even you have this kind of dishes at your home antennas or a television set. So it's basically radio telescopes. These are bigger in size. But not only this, you might have this kind of antennas also, which are basically called dipole antenna, or you might have this kind of cylindrical antennas. So you have different kind of radio telescopes. And this has a parabolic shape. And it's very interesting. These are not circular and why it's parabolic, because whenever radiation is coming from outside, from the space, it's almost parallel. And for parabola, if you have studied in class 12 maths, probably, you know that the focus of the parabola, say it lies here. So now if the whatever radiation is coming here, it falls and it goes here. So the distance, so this from Q1 to R1 to F or Q3 to R3 to F, this distance is the same. So as a result, this detector, this small object is placed at the focus of this disk. And as a result, whenever radio waves are falling here, at the receiver, all the radio waves will be detected at the same time, and you no longer have any lag. Had you put it in other place, your path difference will be different and you will have a lag. So that's why for these are parabolic in shape and not circular, because circle doesn't have such a property. So it's very interesting phenomena why this is a parabola. So again, one more thing, probably you've seen, I don't know if you've seen, radio telescopes are not only, sometimes you have like this, just one dish, but sometimes you have many dishes here. Okay. Why is it so? Because radio waves are longer in the radio waves have longest wavelength. As a result, sometimes just one single dish cannot detect the whole of this wavelength. As a result, you need to build a big telescope, say for example, 10-kilometer big telescope. But that's not possible. You cannot build a 10-kilometer big dish, right? So as a result, we build small dishes. They are spread around on this, say for example, 10-kilometer side at different places, and then you observe the signals from all these dishes, and then you started doing some correlation algorithm, and that's how we can finally can detect the object. So the Event Horizon Telescope, that the image of the black hole I showed you at the beginning, that was also detected by some radio telescopes, which are placed all over the world. You can see one is placed at the Antarctica, some in US and Europe and all these places. And later, when it takes the radiation, after that we just match. They just match all the data, which is called correlation algorithm, and with that we finally have the image of that particular black hole that you have seen. Okay. Now in South Africa, we have something called HIREX telescope, which is currently in build. We still have like 8 dishes or so, but in a couple of years, we will have 250 dishes. And that's what I'm a part of. And HIREX means Hydrogen Intensity and Real-Time Analysis Experiment. So eventually it would look like something like this. So you have this many radio telescopes will be placed here, and it will operate on 400 to 800 megahertz. And this is very interesting. Like this name turns out to be HIREX, and HIREX is basically an animal, which generally we have seen in South Africa. And this HIREX, that's how this logo is coming from, this animal. So there are many science goals that HIREX will be doing in the future. One is something like it will start detecting some dark energy, basically some intensity mapping. Then it will start detecting fast radio bursts and pulsars and some other things also. So that's why HIREX is currently one of the very interesting goal in the scientific community, and many people are trying to basically involved in this project. Okay. So yeah, that basically ends my talk. So this is just a small summary I'm just putting. So basically, physics of compact objects is very important to understand many astrophysical phenomena that I have said, even not only white dwarf, fast neutron star and black hole, but also the other objects that we have seen. And of course, not only one single wavelength, say for example, not only optical telescope, not only radio telescope, or not only gravitational wave telescopes is important. You need to observe as many objects as possible in all the different wavelength, multi-wavelength astronomy, and also in gravitational wave astronomy. Also, neutrino observation is quite important. So these are basically some of the things that currently people are working on. Multi-wavelength astronomy is a very hot topic in astrophysics field. So if somebody wants to pursue some research, it's quite an interesting path actually. Okay. So for any queries, you can now ask me some questions, whatever you have doubt. And of course, in the future, if you have some doubt regarding any of these academic things also, you can write to me in this email ID. So yeah, thanks a lot.
Yeah, thank you, Surajit, for your excellent talk. You covered a lot actually, starting from the very basics of compact objects to the current research areas in this field. So now the floor is open for questions. So you can unmute yourself and ask, or you may also write in the chat box. Yeah. Yeah, I see one audience unmuting himself. You may ask your question. Yeah. So no one has
I
any
cannot.
question. Yeah, I can see a question in the chat box.
Okay.
So let's see.
Okay, can you read me the questions? That might be easy for me.
Yeah, 1 second.
Okay. Okay. Which factor makes a non-rotating black hole rotating? Um, uh, so basically, which factor makes a, I can hear echo a lot. Uh, so which factor makes a non-rotating black hole rotating? So it's basically factor means, see, it's a rotation. It's already there. It doesn't make, you need, it's not like an object currently I have and in the future I'm just starting to rotate. Every object in the universe is rotating. So for example, at our very beginning level, we used to learn, for example, sun is static and earth is rotating. But we know that sun is also not static. It's also rotating in the galaxies. Similarly, galaxies are rotating. So none of the objects are rotating. So I don't know what exactly you want to ask, but all the objects are rotating by themselves. Okay.
Hello.
Yeah.
Thank you, sir. Yeah, thank you, sir. But you said that there are some rotating black holes and non-rotating black holes. Then what is that
Mhm.
non-rotating black holes?
Oh, no, no, no. So I mean to say, it's a theoretical idea that what will happen if you have non-rotating black holes. In reality, no black holes are non-rotating. So that's every object is rotating. Similarly, every white dwarfs, every neutron stars are rotating. You don't see any of them are non-rotating. But to understand about that rotation, you first need to understand about the non-rotation. That's why we did all this. I showed you all the calculations at the beginning. And that's why even in Chandrasekhar at the beginning, he did only use only non-rotation. But in the universe, none of the objects are non-rotating. Everything is rotating. Okay. So you need to, for proper astrophysical simulation or to match with observations, you need to do everything in terms of rotation. Okay. You cannot do a non-rotation and then match with the observation.
Okay, sir. Thank you.
Pleasure. Then Marina after us, why do some massive stars become neutron stars? Okay. As I have said, in this slide, that see, if you have less mass of the star, when you have this red giant phase, your core has already, hydrogen is over, so helium burning is going on. And towards the surface, still hydrogen burning is going on. But because it has less mass, its mass is not that high. As a result, its gravitational pull is also not that high. As a result, this outside portion is detached and the inside becomes a white dwarf. But what happens for neutron stars? You have the core, again, the same thing. You have this outside thing. But because now core has more mass, because it's massive object, right, compared to what this one. As a result, all these objects are suddenly pulled together, and when it pulls together, it increases the temperature instantaneously quite a lot, and it becomes supernova. and the core remains. Okay, now let's understand how high this mass is, because probably you need to understand what will become neutron star and what will become black hole. Suppose you have mass, say 15 solar mass. In that case, it's still collapsing. This core is collapsing, but it's collapsing up to some pressure where basically um, your gas pressure, your gravity is still there, but this gas pressure is balanced by some neutron regeneracy pressure. So neutrons are putting some pressure, also some other particles. But if you have more mass, then even this gravity still wins. So neutrons cannot balance. As a result, in that case, if you have more mass than this, then this gravity wins and everything still collapsing and collapsing. And as a result, you finally get a black hole. Basically, everything collapses together. And basically, you don't have any more fusion, because probably you know in high energy physics that fusion occurs maximum up to generally iron. Okay, so the iron is already achieved in neutron star, so it doesn't fuse anymore. As a result, basically whatever object is there, that's falling inside of this event horizon and it becomes a black hole. I hope it's understandable. What happens do other objects have any direct impact? Okay, second question, no. Have any direct impact on humankind? Definitely no, not so far we have observed anything, because they are quite far from us. The first question is, what are the final stages of white dwarf, neutron star, and black hole? For white dwarf, as I said, once you have white dwarf, but eventually if it has some other objects, it will become type 1 supernova, so it bursts again, and nothing, basically it shatters away, so white dwarf is no longer there. But for neutron stars and black hole, we still don't know the final outcome. So that's basically the final stage we all know. We have never seen, basically neutron stars still become a black hole. Suppose two neutron star merge and it becomes a black hole. But whatever current observations we have, so even if we merge two black holes, it will become another black hole. So basically black hole is the final stage, you can say. How people measure mass of...
Yeah.
Sure, yeah.
Yeah, go ahead. Yeah.
Oh, okay. How people measure mass of these stellar objects. Okay, there are different methods. One is basically spectroscopic method, and what is it? Let me show you. Okay, for mass of the black hole, you can measure it from this image itself. Because you have seen this image, you know the radius of this object, and once you know the radius, I'm just showing it for non-rotating. For rotating also, you have some formula. So once you know the radius, you can obtain basically the mass. It's not quite difficult. And also with this accretion, these things also people have observed what's there inside, because you know how basically power of jet and all these things are very much related to what's inside here. So accordingly, these things are measured. And for white dwarfs and for neutron stars, basically you obtain this kind of spectroscopic feature. That means you observe these things of spectroscopy. Another important thing is you see most of these things in binaries. That means two objects are rotating around each other. Say like this, say, for example, two white dwarfs are rotating around each other. You see many of them. In such a case, you basically, it's pretty simple. When two objects are rotating around each other, you can get basically some classical mechanics you can use here, and you can obtain basically the mass of the object. You will see lots of precision and so on. So all these things can be used to measure the masses of this object.
Then, there is another question about the heavier element form in the universe, such as gold.
Mm-hmm.
Yeah.
Yes. How are heavier elements such as gold formed in the universe? Sorry, how are heavier gold formed in the universe? Okay, these are These do not form inside and compact object. These are formed in different elements, different other objects also. Of course, you have also something called cosmology. So in cosmology also, there are different phases of the universe where you basically have different elements, and then you obtain basically fusion reaction happens and so on. So in that way, basically you basically obtain these heavier elements at the first phase, and of course many of these are also artificially made. But yeah, like gold and all these things will come from, say, for example, in comets you have all these things, or uh, some other objects, basically. Yeah. So, okay, the one is
So Ranjan is asking about your work in details.
okay. I don't know what I should say about my work. Uh, you can read everything in my papers, but I cannot say in detail right now because that will be like hours of talks. But but in briefly, I study about gravitational waves. I study white dwarfs objects, all this, how it deforms in the presence of magnetic fields, rotation, all these things. Or I also study something called fast radio burst, even its observations and so on. But probably I cannot say in detail right now because of time constraint. I'm sorry for that.
Yeah. And then Nikita is asking, can black holes get smaller?
What do you mean by smaller?
Yeah, smaller by size or
Small?
mass? Yeah.
Yes. What do you mean? I mean, do you mean to say black hole of size of say 1 kilometer or 1 millimeter, something like this?
Yes,
Nikita,
sir.
you may specify. I mean, by smaller, what do you
Okay.
mean? Yeah.
Okay, I got it. So, okay, there are one interesting aspect that I did not speak here.
Probably
So
she is
black holes
asking
are,
about this Hawking radiation. Yeah.
yes, that's what I'm also going to say. So
Yeah.
basically, as I said, these are basically stellar mass black holes that have been observed. But people propose much lighter black holes, a fraction of mass of the sun. So how to obtain those masses? They cannot also be formed by the stellar objects. So it's very doubtful. So we generally propose something called primordial mass black holes, and so yes, they can have much smaller in mass, of the order of 10 to the power minus 14 solar mass or so, because you cannot get much smaller than that, because those are basically Hawking radiated because of our universe age. Basically, we can get that idea. But yeah, you can get it, and once you get the mass, you can get the size. So you know if it's 1 kilometer, one solar mass black hole, its mass size is 3 kilometers. So probably you can understand if I say about 10 to the minus 3 mass of a black hole, the solar mass of a black hole, then its size is smaller. So yes, in principle you have, but we have not detected any of them so far.
Yeah. So Bikram has another question. Where does all the objects that gets absorbed by black hole go? Okay.
That's inside the black hole. You don't know what's inside there. So black holes can grow, actually in principle grow mass, okay, in time. So you can get basically black holes increase its mass, but the problem is that increase in mass is quite slow. You don't see any significant difference. That's what. But another thing I want to mention, say for example in jet-like feature, probably you might think that these kind of jets are coming out of the black hole, but it's not. It's still these objects which are falling inside. Part of it are actually going outside, and those we see as jet. It's nothing which is coming inside of this short cell radius or so. Okay.
So there is
Okay.
another
Next
question
question.
about, yeah.
Neutrino observations will understanding. Okay. So, what are neutrinos? Of course, I don't have much time to say about these things, but neutrinos are also some object which initially thought to be massless, but we know that they have mass. And neutrinos can change its identity when it's traveling. Okay, so you have something called solar neutrino and stellar neutrino. So some neutrinos are coming from sun. In such a case, the neutrinos are basically there are different kind of neutrinos. Say type 1 neutrino becomes type 2 when it's coming to Earth, and once you detect it from this by this neutrino observatory, in the few you would probably know what's there in the sun. So initially, basically, we used to think just one kind of neutrino, but only after neutrino observations were done, we came to know that neutrinos have masses, neutrinos have different flavors with different types, and yeah, so that's how we know about neutrinos. And another thing is that photon, say for example, say for sun, hydrogen burning is going on. So photon needs more time to come out of the sun. Okay, but neutrinos, because it's less interactive with the matter, it can come out of sun or any other object quite easily, and that's why neutrinos can travel much farther. And that's why it's very difficult to detect, and you can understand much farther object and much inside of what's inside, say for example, in our sun.
Yes. There is another question about what happens if a person fell into a black hole. Would have any chances of survival? If then,
The
how
answer
you
is
get out of it?
answer is we don't know. We don't know because they are quite far, and that's quite imaginary. And one more thing I want to say. So suppose you are falling here. Let's say I'm assuming you're falling. You cannot see person falling inside because for you something there is an idea of time dilation. So you need infinite amount of time to see if the person is really falling inside the black hole.
Dixit is asking, sir, what are the advantages of Hyrax telescope over our normal radio telescopes?
Okay.
And can you briefly explain? Yes.
Okay, yes, that's a good point. So what happens, because I've said about this first radio burst. So what happens, first radio bursts were first discovered in 2007, and still 2020 probably, we just discovered only 50 of those first radio bursts. Okay. Because first radio bursts are quite random and no radio telescopes are dedicated in such a way, so whoever accidentally have detected it, that's all. But what happens, recently, something called SIME radio telescope have been built and in Canada, and it has detected over 600 FRBs. So similarly, our Hyrax telescope, but see, Canada is in northern hemisphere. We need something for the southern hemisphere, and for the southern hemisphere, this Hyrax will be a complementary to SIME radio telescope, and it will also observe lots of fast radio bursts and also pulsars. So one advantage is that, of course, it can observe these fast radio bursts compared to other radio telescopes over the world. The second thing is something called 21 centimeter intensity mapping. So I don't know how to tell you in short in these things. It's basically something called baryonic acoustic oscillations that were there at the time of early universe after Big Bang or so, for inflation actually. So in that thing, basically, Hyrax will eventually able to detect baryonic acoustic oscillations, BAOs, and BAOs would be useful. I don't know if you probably don't know. Like I said initially, I was talking about type 1A supernova are used as standard rulers to measure distances, but there are some problem in this idea. So in the future, people are trying to replace that idea with respect to baryonic acoustic oscillations. And in such a case, basically, Hyrax would probably help. We are expecting that.
Okay. So any more questions from the audience?
You can directly ask also, not to write.
Yeah. Just unmute and you can just ask.
Sir.
Hello, sir.
Yeah.
Hello. Yeah. Sorry. Out of curiosity, I just want to ask you, how do you get to know that the sun and the black hole are related? I mean, when the sun gets high mass, then supernova happen, then it becomes the black holes. But how do you know that the sun and this black hole are interrelated?
So sun and black hole are not that. Sun needs to be like at least 25 solar mass units. Sun and white dwarfs are related. Okay. So
Yes, sir.
so of course we don't know. That's one way because this happens in millions of years. So you need computer simulations for this, where basically you know some of the property. We know some properties of sun, we know some properties of red giant, we know some properties of this, and we know some properties of that. Now we accumulate all the properties we know, and then we ask our computer simulation to run through all these things, and then we see what will happen. So for even HR diagram, it's quite useful. See, for example, you can see, so an object is here. Eventually, it becomes, it's like a joint. You can see it's like nicely joined here, and there are a few more here basically. And then slowly it becomes here, and it comes here. Okay. So we see this kind of joints also in HR diagram. Actually, there are more numbers now. So this joint is quite nicely visible now. So because there is a joint, that means there should be some property which are basically, I would say, collecting or connecting these objects, white dwarfs, and say sun, say main sequence star. In that way, we will know. And exactly what mass will become, that of course computer simulation. And that's why I said we still don't know the exact bounds here. So sometimes 10, some people say 11, 12, or 8 or so. So yeah, but that's the way we know.
Okay. So any more question? Yeah.
Hello, sir.
Yeah.
Sir, as you mentioned about that Hyrex technology and that baryon acoustic oscillation, sir, I am a first year student, postgraduate student, so I don't know much about cosmology or high energy physics. But sir, will it help us to give more information about dark energy and dark matter, this Hyrex technology and that the term you mentioned, baryon acoustic oscillations?
Yes. So, of course, one is, I don't know about dark matter, it will help, but definitely on dark energy, it will help. But of course, we know the fraction already, roughly it's 5%, 26%, and that. So that needs no revision as such, a little bit. But apart from that, what kind of, see, dark energies are something that we observe now. I mean, our universe is experiencing now, right? We don't know exactly what are the properties of it because we have not directly detected. Of course, it probably will not detect, even Hyrex cannot detect dark energy as such, or even dark matter. But probably because it will detect something called baryonic acoustic oscillation, which happened at the after inflationary era, where basically universe were also expanding, and probably that was the phase where basically your dark energy on all these things were started, basically something called radiation dominated era and so are there. So thereby probably in the future we will able to know about these things. So in that way basically Hyrex should help. But exactly like what are the properties we will detect or so, probably we still don't know, or even probably I don't know, that's another possibility.
Yes,
Yes, sir.
probably it will not, I mean, we will not be able to know any particle nature of dark matter out of this Hyrex, but yes, but the fraction of these energy densities, maybe we may know
Yeah.
it from this new result.
Yeah.
I mean, that we
Yeah.
already know, but yes.
Yeah, but maybe some corrections, or maybe it's just a
Some corrections
verification.
may
That's
come.
all. Yeah. But that actually baryonic oscillation have not been observed because baryonic oscillation is related to Deborah, probably you know after inflation you have before that hydrogen were formed, that basically some
Recombination era, yes.
recombination era before that, yes. And in that phase, basically some oscillations were there of some particle or
Yes,
some
yes.
objects. And that's basically people are thinking to use as more standard ruler and more sophisticated and stuff.
Sir,
Yeah.
sir, I have another question. Sir, as you mentioned, or as we know that supernova or stars like or other stars like behave like some standard candle in astronomical observations.
Mhm.
Sir, in near future, will this BAO technology or Hyrax technology will completely replace that in in astronomical measurement or cosmological measurement?
So not completely. I will not never say completely it will replace, but yes, some portion it will replace. So
Yes, sir.
one is of course, see so far what we have two particular standard candles at present day. One is of course this type 1 is supernovae, and another is something called Cepheid variable stars. But Cepheid variable stars are useful to detect distances little bit nearby objects. But these, because of luminosity and these things, we can also probe it to some cosmological objects like far objects where redshift is quite high. So like DOs will come. So I don't think DOs will completely replace, because see in between, so maybe DO will replace you much farther distance object. So you might get some corrections, but some of the objects things we know from Cepheid variable stars as well as from standard I mean from type 1a supernova, that's its distance. So if we know some distance, probably VOs will just confirm that's the thing. But at larger distance, it might replace little bit. I mean, it might give you. So it will partially replace, but not, I believe, completely.
Okay, sir.
So that's quite an interactive session we had today. So any more questions? So if not, then so are you running out of time, Surajit? So if not, I
No,
will
I'm
just,
fine. I'm fine. I don't have
okay.
I do. It's holiday here today.
Same here, yeah. So I just have a nice question probably. So in your hydrostatic
Mhm.
equilibrium equation, I do not see any theory of gravity entering there, but you showed that the results are different if we consider Newtonian gravity and GR. So how
Yes.
the gravity theory of gravity is entering in? I mean, I could not get it.
Uh, See, theory of gravity means, first of all, this is Newtonian, right? And this is for GR, this TOV equation.
I see. In the
Uh,
pressure equation, yes. So,
Yes, pressure equation itself is modified. Now, if you take, say, rho is larger than P, mass is larger than P, and this factor is there, then it replaces, it goes here. Okay. So in this way, this is basically the thing. Now, if you say gravity theory, it also gives you a larger perspective, because we no longer have, I mean, not only have general relativity, but we have something also modified gravity that people are working on. I also work on. So you have some modifications on Einstein theory of gravity, GR. So then these equations are also modified. These two equations modified. Then your mass radius curve will again modify according to which theory you are considering. Okay.
I see. And another question is like you told that event of white dwarfs are cold, but still their temperature is greater than the temperature of the sun.
Yes.
But how this thermal energy is being generated? Do this Fermi degeneracy can lead to
Yes.
such high temperatures?
Yes. Because already, see, uh, so already the core is here, right? At the core, you have still have carbon and so on. All these things are material, right? So
Right.
they already have some residual energy already, right? So that residual energy we generally see as surface energy, surface temperature.
So residual energy means it is the thermal energy which is like being stored. Is it like that?
Yes, yes. Yeah.
So is it not due to the Fermi degeneracy then?
No. Because Fermi degeneration, basically what is there, it's basically just electrons are degenerate, right? The protons and all these things are
Yes,
still there. And electron-electron interaction will not generate that much of energy, even if they collide at some point. So it's equivalent of almost nothing.
So will not these heavier atoms I mean, they don't lose energy over time if a white dwarf is
Oh,
settled?
yes. Yes. Actually, you need to do for that exact calculation. So there are important ideas, which is basically if you have magnetized white dwarf, suppose you have magnetic field. So through magnetic field lines, also, I mean, if you, how would I say? Okay, one is of course with respect to time, its temperature will decrease. That's one story. But another thing is more than that, people are more interested on magnetized white dwarf versus or highly magnetized versus lowly magnetized white dwarf temperature. If you have high magnetic field, those white dwarfs generally have less temperature than the less magnetized white dwarf, because some thermal energy are contributed in the magnetic energy. In that way, thermal energy decreases, and as a result, white dwarf becomes little bit of colder. Okay, but then again, people generally check how magnetic fields are decaying, because magnetic field decay is much more important, right? So once a magnetic field decays, then also temperature will also it will affect the temperature, and that way basically temperature also changes over time.
Okay. So this is still, I mean, active research area, I mean, I guess.
Yes, yes, yes. We have studied also in my PhD, and currently people are also studied
Okay.
for that.
Okay.
Yeah.
Thank you. So, are there any questions? So, if not, let's thank the speaker for his excellent talk and the discussion session.
Yeah. It's nice talking to you, David, and the others. Also, thanks for attending.
Yeah. So then I would like to request my colleague, Dr. Santanu Kaur, to end the session with his concluding remarks. Yeah.
Okay, thank you, Deborah. So first of all, I should thank the speaker, Dr. Surajit Kalita from Cape Town University, South Africa. Also, before giving the concluding remark, I should also thank all the participants, those who are from outside Assam also. I'm very happy to see that it's going to be a national one, means we are getting participants from outside our state also. Anyway, it was indeed a very beautiful talk. Means very simple deliberation of some complicated things and very interesting things. So I personally, though I am not from the field of cosmology, but I personally could get some new ideas, means about the different topics. Also, a lot of questions are running around my mind, but I'm not, means I don't think that I should ask all the questions here. The session should be confined within some time limit. So later I'll discuss with developer, that will be the better solution. Anyway, so it was a very beautiful explanations and some beautiful insights on three main topics. That was compact stellar objects, that is white dwarf, black hole, and the neutron star. Moreover, the speaker had also covered the gravitational wave and radio telescope, two of the most warm or hot topic recently in recent years. The interaction of the participations was also very good and encouraging. So I think by this, if we proceed in this way, we can get up to the main motive of our lecture series, so that the students, mainly the undergraduate and postgraduate students, can have some idea what to do after their studies, in what areas people are working in physics and related science. So I also thank mainly Deborah and Dipsika for the initiative. I am joining for the first time in today's lecture itself, because I was very busy these days. Anyway, thank you both of you for organizing such beautiful lectures. And thank you once again to our speaker, Dr. Surajit Kalita. Thank you.
Yeah, thanks everyone.
Thank you, sir.
Okay, this is all from my part. That was the analysis. He left. Okay, with this we end our today's. Thank you, everyone.